Once acetylcholine has bound to its receptor and opened the sodium channel, the signal must be terminated cleanly and rapidly. This is accomplished by the enzyme acetylcholinesterase, positioned directly within the postsynaptic zone, right in the synaptic cleft at the end plate. The moment acetylcholine finishes binding, it is immediately hydrolyzed, broken down into choline and acetate before it can rebind or continue acting. This rapid enzymatic inactivation is not simply a cleanup mechanism, it is functionally essential. Without acetylcholinesterase acting at high speed, acetylcholine would remain in the cleft, continuously activating the receptor, keeping sodium channels open, and preventing the muscle from ever relaxing. The neuromuscular junction depends on this precise, fast termination to allow high-frequency signaling without signal summation or unwanted sustained contraction. This mechanism is also why drugs that inhibit acetylcholinesterase, called anticholinesterase agents, are therapeutically useful in myasthenia gravis. By slowing acetylcholine breakdown, they increase the time acetylcholine spends in the cleft, improving the chance of successfully activating the diminished number of functional receptors remaining after antibody-mediated damage. The same principle applies in the opposite direction to toxins that overactivate cholinergic synapses by preventing acetylcholine breakdown. The result is a cholinergic crisis with excessive, uncontrolled muscle activation. After acetylcholine is released and activates nicotinic acetylcholine receptors, acetylcholinesterase in the junctional cleft destroys transmitter molecules that do not bind or that dissociate from the receptor, limiting each acetylcholine molecule to a very brief action. Acetylcholine action at the neuromuscular junction is extremely short-lived. Sources describe destruction in less than 1 millisecond and hydrolysis in about 80 to 100 microseconds, which prevents continuous end-plate stimulation. Junctional acetylcholinesterase is concentrated in the synaptic cleft end-plate region and is attached to the basement membrane. Lower concentrations are present extrajunctionally. Metabolism of acetylcholine permits sarcolemma repolarization and resets the muscle fiber for the next depolarization contraction cycle. Organophosphates and nerve agents prevent acetylcholinesterase from hydrolyzing acetylcholine, causing acetylcholine accumulation, receptor overstimulation, excess secretions, smooth muscle effects, and cholinergic toxicity. Therapeutic acetylcholinesterase inhibition increases acetylcholine at the neuromuscular junction and can reverse non-depolarizing neuromuscular block or improve myasthenia gravis symptoms, but excessive inhibition can itself produce weakness from persistent depolarization and cholinergic adverse effects. In the next video, we will go over Lambert-Eaton myasthenic syndrome, mechanism, and clinical features.